Namaste, my friend, and welcome back to JEE Physics with Typical Monk. This is Class 7, and today we leave straight line motion behind and enter the world of spin. Every object that turns, a wheel, a door, a planet, a rolling ball, obeys the same two ideas: torque, which twists, and moment of inertia, which resists the twist. 9.8 meters per second squared told us how a block slides. Today, tau equals I alpha tells us how a body spins. Sarah once treated a ball rolling down a slope exactly like a block sliding down it and lost the entire question because a rolling body carries two kinds of motion at once, moving forward and spinning around its own center. Today we untangle both, together, one idea at a time. Take a slow breath. Let us begin. So what will you carry home from today's class? First, torque and angular momentum, the rotational twins of force and momentum. Second, moment of inertia by integration, the thin rod, the disk, and the parallel and perpendicular axis theorems that let us shift between axes. Third, rotational kinematics and dynamics, tau equals I alpha, the rotational version of Newton's second law. Fourth, rolling without slipping, how kinetic energy splits into a translation part and a rotation part. And fifth, conservation of angular momentum, exactly when it holds, and how a spinning skater speeds up by pulling in her arms. Ready? One idea at a time. Now, easy meet the four ideas that run through this whole class. Torque is R cross F, a force applied at some distance from an axis, and it is torque, not force alone, that spins a body. Moment of inertia is the integral of R squared dm, every little piece of mass, weighted by the square of its distance from the axis. This integral is the calculus that G loves and NEET mostly skips. Angular momentum is I omega, mass in motion around an axis, the rotational twin of ordinary momentum. And rolling kinetic energy is 1/2 mv squared plus 1/2 I omega squared. A rolling body is never just translating and never just spinning. It is always both at once. David used to add these two energies by guessing. Once he learned they are simply added term by term, he never guessed again. Look at this diagram carefully, because torque and angular momentum grow out of each other. In the center sits torque. Torque equals R cross F, or RF sine theta, a force applied at some radius, twisting about the axis. This is where the spin begins. Torque also equals I alpha, mass distribution times angular acceleration, the exact rotational twin of equals ma. Now angular momentum. L equals I omega, moment of inertia times angular velocity, the rotational twin of ordinary momentum, mv. And here is the deepest link. Torque is the rate of change of angular momentum, tau equals dl by dt. This single line is why angular momentum stays constant the moment torque disappears. Lisa used to think torque and angular momentum were two separate topics until she saw that one is simply the time derivative of the other. Now, how do we actually calculate and connect these ideas? First, rotational kinematics mirrors linear motion equation for equation. Omega equals omega naught plus alpha t. Theta equals omega naught t plus 1/2 alpha t squared, and omega squared equals omega naught squared plus 2 alpha theta. Just replace displacement, velocity and acceleration with angle, angular velocity, and angular acceleration. Second, tau equals I alpha is Newton's second law for rotation, with moment of inertia playing the role mass played before. Third, the parallel axis theorem, I equals I about the center of mass plus md squared, whenever you shift the axis a distance d away, parallel to the original. And fourth, the perpendicular axis theorem, I about the z-axis equals I about x plus I about y but y, but only for a flat, planar body, with x and y in the plane, and z perpendicular to the same point. John kept using the perpendicular axis theorem on a solid sphere, and it simply does not apply there. It is only for flat laminas. Time to solve a full G numerical, together, slowly, the monk's way. A solid sphere of radius r, rolls without slipping down an incline of 30 degrees with g equal to 10 meters per second squared. Find its linear acceleration down the slope. Step 1. Write down what is given. A solid sphere, rolling without slipping. Incline angle 30 degrees, g equal to 10 meters per second squared. And its moment of inertia about its own center, 2/5 mr squared. Step 2. The formula for a rolling body on an incline. Acceleration equals g sine theta divided by 1 plus I over mr squared. The extra term in the denominator is the price of also having to spin. Step 3. The I over mr squared term. 2/5 mr squared over mr squared is simply 2/5, which is 0.4. Step 4. The denominator 1 plus 0.4 is 1.4, which is 7/5. Notice this denominator is exactly why a sphere never accelerates as fast as it would if it only slid without rotating. Step 5. Put it together. G sine theta is 10 times 0.5, which is 5. 5 divided by 1.4 is 25 over 7. Approximately 3.57 meters per second squared. That is your answer. And the same 4 moves. Formula, the I over mr squared term. The denominator, then divide, solve every rolling incline numerical G can ask. Now, the shapes themselves. Because G loves asking which body has which moment of inertia, and how that decides a race downhill. First, the thin rod. About an axis through its center, I is 1/12 ml squared. About an axis through its end, I is 1/3 ml squared, 4 times larger, because more mass now sits far from the axis. Second, the round shapes. A disc or a solid cylinder about its central axis carries 1/2 mr squared. A solid sphere about its diameter carries 2/5 mr squared, smaller because a sphere packs its mass closer to the center. A ring about its central axis carries the full mr squared, every bit of mass sitting at the rim. Third, rolling without slipping ties the two motions together through one equation, B equals omega r, and therefore A equals alpha r as well. And fourth, kinetic energy splits into 1/2 mv squared for translation, plus 1/2 I omega squared for rotation. And the smaller a body's I over mr squared ratio, the faster it wins the race downhill. That is why, released together, a solid sphere always beats a disk, and a disk always beats a ring. John once bet on the ring in a lap race, and the sphere had already reached the bottom before he finished placing his bet. Now sit up straight. These 5 lines are what G actually asks year after year about rotation. 1. Tau equals I alpha and L equals I omega are the rotational twins of force and momentum. Know the moment of inertia of a rod, a disk, a sphere, and a ring called. 2. The parallel axis theorem adds md squared when you move away from the center of mass. The perpendicular axis theorem only works for a flat planar lamina. 3. In a race down an incline, the body with the smallest I over mr squared ratio always wins, sphere, then disk, then ring. 4. Angular momentum is conserved whenever the net external torque is 0, even if the moment of inertia itself changes, exactly like a skater pulling in her arms. 5. In rolling without slipping, the friction at the contact point is static, and the contact point is instantaneously at rest, so friction does 0 work, energy stays conserved. Let us drill the G way. Remember the 4 options. Option A, both statements true, and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion. A solid sphere reaches the bottom of an incline before a ring of the same mass and radius, when both roll without slipping. Reason, the sphere has a smaller moment of inertia about its central axis than the ring. Think like Sarah. Check each statement, then the connection. Is the assertion true? Yes. Is the reason true? Yes. And does the reason explain the assertion? perfectly, the smaller moment of inertia is exactly why more of the sphere's energy goes into translation. Both true. Reason explains. Option A. Second one. Assertion. The moment of inertia of a rod about an axis through its end is 4 times its moment of inertia about a parallel axis through its center. Reason. Moment of inertia depends on the square of the distance from the axis. Both statements are true. But pause. Does the reason explain the assertion fully? Not quite. The exact factor of 4 comes from combining the parallel axis theorem with the rod's own values, not from the r-squared dependence alone. Both true, but the reason does not fully explain the assertion. Option B. This is the trap that catches David every time. Third one. Assertion. The angular momentum of a rotating body is always conserved. Reason. Angular momentum is conserved only when the net external torque on the body is 0. Check the reason first. True. Angular momentum is conserved only under 0 net torque. Now, the assertion, always conserved, is false, because most real bodies do feel some external torque, like friction or gravity. Assertion false. Reason true. Option D. A quick match now. Say each moment of inertia aloud before I reveal it. Thin rod about its center, 1/12 ml squared. Disc or solid cylinder about its central axis, 1/2 mr squared. Solid sphere about its diameter, 2/5 mr squared. And ring or hoop about its central axis, the full mr squared, every bit of mass at the rim. If all 4 came to you before the reveal, the table is becoming yours. Use a favorite G format. I will read some statements. You silently count how many are correct. Statement 1. A solid sphere, rolling without slipping down an incline, reaches the bottom before a hollow sphere of the same mass and radius. Hold your verdict. Statement 2. The moment of inertia of a body about a given axis depends on its mass, its shape, and its angular velocity. Think carefully before you answer. Statement 3. If the net external torque on a system is 0, its angular momentum stays constant, even if its own moment of inertia changes. So, how many are correct? 2 statements, the first and the third. A solid sphere truly has a smaller moment of inertia than a hollow sphere of the same mass and radius, so it accelerates faster and wins. An angular momentum truly stays constant under 0 net torque, even while moment of inertia itself is changing, exactly like a skater pulling in her arms. But the second one falls. Moment of inertia never depends on angular velocity, only on mass and how it is distributed about the axis. 2 correct, and the middle one is the trap. Now let me save you some marks. 2 myths that trap thousands of students every year. Myth 1. Moment of inertia is a fixed property of a body, like its mass, and never changes. But here is the truth. Moment of inertia depends on the axis of rotation and on how mass is spread about it. The very same rod has a different I about its center than about its end. Myth 2. In rolling without slipping, friction drains energy the same way kinetic friction always does. The truth? The friction at the contact point is static, and that point is instantaneously at rest, so it does 0 work. Mechanical energy stays fully conserved in ideal rolling. 1 myth, 1 full G question. Do not let it be the one that costs you. Time to test yourself, rapid fire, and every answer today is a number. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just what you built today. Question 1. A solid sphere of mass 2 kilograms and radius 0.5 meters. Its moment of inertia about its diameter 2/5 mr squared, which is 0.2 kilogram meter squared. Question 2. A torque of 10 Newton meters produces an angular acceleration of 2 radians per second squared. Its moment of inertia, torque over alpha, 5 kilogram meter squared. Question 3. A flywheel with moment of inertia 4 kilogram meter squared spins at 5 radians per second. Its angular momentum, I omega, 20 kilogram meters squared per second. Question 4. A solid cylinder rolls without slipping down a 30-degree incline, with g equal to 10 meters per second squared. Its linear acceleration, g sine theta over 1 plus 1 half, which is 10 times 0.5 over 1.5, 3.33 meters per second squared. And question 5. The thinker. A skater spins at 4 radians per second with moment of inertia 2 kilogram meter squared, then pulls in her arms until her moment of inertia becomes 1 kilogram meter squared. Her new angular velocity, angular momentum is conserved, I1 omega 1 equals I2 omega 2, so 2 times 4 over 1, 8 radians per second. If you caught that one, you have truly understood today's class. Let us gather the whole class in one slow breath. Torque, tau, equals I alpha, and angular momentum equals I omega are the rotational twins of force and momentum. Moment of inertia comes from the integral of r squared dm and depends on the axis. The parallel axis theorem adds md squared. The perpendicular axis theorem works only for a flat lamina. Rotational kinematics mirrors linear motion equation for equation, with theta, omega, and alpha replacing displacement, velocity, and acceleration. Rolling without slipping locks, B equals omega r, and kinetic energy splits into translation, 1/2 mb squared, and rotation, 1/2 I omega squared. Angular momentum is conserved whenever the net external torque is 0, even while the moment of inertia itself changes. And next class, we lift off into gravitation, Newton's law of gravitation, gravitational potential, escape and orbital velocity, and Kepler's laws of planetary motion. This is where rotation meets the cosmos. Do not miss it. And so, my friend, we have learned to see the spin behind every motion. It may have looked like just torque and moment of inertia, but understand this: every wheel, every planet, every rolling ball obeys exactly what you learned today. Sarah, David, Lisa, and John all started exactly where you are right now, with this one class. Be patient with yourself. Tonight, revise the moment of inertia table once, slowly, rod disk, sphere, ring, and say tau equals I alpha, L equals I omega until they feel like your own name. One idea at a time, you will crack G. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you among the planets.